Good afternoon, everybody. Konnichiwa. My name is Kening Zhu. I'm currently working in the School of Creative Media, City University of Hong Kong, as an assistant professor. And today I'm very happy to share with you some of the works I have done, which is mainly focusing on human-computer interaction, which is inspired by our interaction with paper crafts, such as folding, coloring, etc., etc. So to start, just give you, I guess most of you are very familiar with paper, especially in Japan. You have really rich culture of paper crafts as well. And also in China, I'm from China, we also have very rich cultural experience with paper, such as folding, origami, or cutting, etc., etc. But when paper was invented, it was mainly used as a medium for recording and or documenting information, such as we print tests on the paper, we write on the paper. When we read something, we do annotation on the paper, etc., etc. And later on, when artists look at these kind of materials, they think that, okay, this could be a very good material of creating artworks. So that papercraft was born. So in terms of papercraft, the information is no longer represented in the form of texts, and it was represented in a more intuitive way, such as colors, shapes, and movements, just like we use our body to express ourselves. And so this is paper, very, very traditional materials. And when we look at digital information medium today, such as screens, laptops, mobile phones, tablets, they share some similarity with paper, such as flat. They are really flat, right? It's getting thinner and thinner. But on the other hand, it's lack of the affordance of paper, such as we can write on it, we can fold it, we can color it, we can scroll them, etc., etc. But most of these devices, we can only point on them, right? So motivating by this kind of problem, actually, not just me, many researchers and scholars and industry in the area of human-computer interaction starts to look at whether we can get some inspiration from this traditional interaction with paper into some digital media. So there are two categories of this kind of interfaces. The first one is paper-based interface. So in this category, researchers mainly use paper as the material, as the interface to interact with the digital information. For example, projecting informations on the paper or embedding digital electronic components into the paper. For example, you see some circuits or LEDs that's embedded in the paper. On the other hand, the second category of paper interface is paper-like interfaces. It's not directly made of paper, but it has some characteristics of paper. For example, we can bend the device, we can fold the device, etc., etc. And recently, Samsung and Huawei released their phone, like Galaxy X and Mate X, which allows you to fold your mobile phones. So what we call this kind of interfaces. They have some similar characteristics of paper. We call them paper-like interfaces. So during my PhD study in Singapore, I actually summarized this work and create a terminology which is called technology-enhanced papercraft. The papercraft, which contains digital technology, and its behavior can be utilized as the input and output methods of an interactive system. So imagine you have a piece of paper, you can use it to interact with the digital information. And the digital information, on the other hand, can also influence the lookings or the interaction of the appearance of the paper. So in my thesis, I have defined three main characteristics of this kind of technology-enhanced papercraft. The first one is the rich interactivity, as well as the high expressiveness. This two characteristic is directly inherited from paper. We know that we can create a lot of different kinds of art form from paper, stuff from origami, painting, paper cutting, paper rolling, etc., etc. It supports a lot of interactions with human. And it's also highly expressive. So we can, as I say, you can create different shapes, create different colors, combinations, assemble different shapes together to create different types of paper crafts. And the third characteristics of this kind of technology enhanced paper craft I define as is a high accessibility. What does it mean? So we integrate technology and paper craft. On one hand, paper craft is really is highly accessible. We can get a piece of paper almost everywhere in our life, and we can do a lot of interaction with them. It's easy to manipulate. But when we integrate technology in it, we don't want to affect this kind of characteristics of paper. So we hope that when we design this kind of technology, enhanced paper craft, we can still keep the intuitiveness, accessibilities of the original material. So along this direction, I actually make a few interactive technologies to support these characteristics of technology enhanced paper crafts. So let me first talk about a project I have done in Singapore during my PhD, which is about how to generate outputs of physical paper craft. So, so this project is called Selective Inductive Power Transmission for Paper Craft. The motivation of this project is, if you look at this existing paper-based interface, you can see a lot of it was integrated with a lot of electronic circuits components. So most of them with these embedded circuits are bulky. It's difficult to end user without any engineering background to design and create this kind of paper craft. So I want to sort of reduce the bulkiness as well as reduce the difficulty of creating this kind of interactive paper craft for most of the users. So I developed this technology called Selective Inductive Power Transmission. Short term is SIFT, to provide electronic powers to paper craft without any wire connection. I don't want to connect any wire to the paper. So I use this inductive technology, and most of the inductive technology is one-to-one. And I modified it a bit. Allows the computer to control the frequency of the magnetic field. In different frequencies, different antennas can be activated so that to transfer the power to different parts of the paper to activate different behavior of the paper craft. So, of course, there is a wireless power transmitter. I won't go into details of the technical parts. And there is also antennas, receivers, which I embedded into the paper. So, and this is one of the experiments I have done. So you have seen that there are 3 antennas here. I can trigger different frequencies to activate different lights. So that means different lights can receive the power at different times. You can control them to light up or on or off in different times to create different patterns. And then and this technology can be easily integrated in the process of pulp-based paper making. For example, you're making a piece of paper using the pulp material, and you can easily embed this antenna into the paper without thinking about how to create the wires and the circuits in the paper material. So this piece of paper is actually wireless and standalone. And when you move it closer to the table underneath with the transmitter, it's receiving the power and can be light up. Okay. And then I start thinking of, okay, I like folding paper since I was a kid. Then whether I can create something that folds automatically by itself, like automatic origami. Then I found this interesting material which is called shape memory alloy, and it changed its shape based on the level of the power it received. So I put it together with the antenna, and I put it on the power transmitter, wireless power transmitter, and it starts receiving power and move by itself. And different parts of the paper can be activated under different frequencies of the signal. So and then I start to do experiments with more well-known origami shape, such as this crane. So this crane can flap by itself when I put it on the table, and it doesn't have any external power source connect to it. So when I fold this paper, I directly put the antenna into the bird, and when I put it on the table, it starts to flap the wing. And this is some of the experiment I have done. And then I was thinking about, I saw that whether I can let most of the users to be able to create this kind of interactive sort of paper craft by themselves. Then I start to I make toolkits that's called Origami. It's automated origami. So it's a low-cost toolkits for creating this kind of paper craft. And this work was published in CAI 2013. And I will show you a video. And this video will contain the narrative by itself.
Papercraft has been widely used in art, education, storytelling, and rapid prototyping. There have been a number of researches focusing in making automated moving paper craft. However, a general toolkit is still in need in terms of the affordance and the usability. We introduced Origami, a low-cost toolkit for automated paper craft using inductive power transmission. Origami toolkit consists of hardware for inductive power and software interface to design paper craft. Origami hardware is based on the technology of selective inductive power transmission. It can power up multiple receivers separately and wirelessly. Shape memory alloy can be attached to power receiver and generate paper movement, such as folding. The Origami software interface supports designing the shape of the paper craft, with various types of basic shapes such as circle, rectangle, and triangle. The software interface also supports designing the parameters of the paper movements. Using Origami, user is able to control the direction of the paper movement. Here we show a demo on simple left-right movement control. The toolkit also supports the control of the amplitude and the duration of the movement. To duplicate the same movement of one part of the paper craft, user just needs to attach the SMA with the same ID to the destinated part. Similarly, movements can be copied from one paper craft to another new paper craft with similar structure.
Maybe I will skip this part and go to the examples created by our user.
Before ending the video, we show the demo of some of the automated paper craft created in the workshop.
This is the toolkit we have made, and we conducted a workshop. As you can see in the video, we actually asked the opinion from the user, and they actually rated it that it's really easy to use the toolkit to create this kind of technology-enhanced papercraft by themselves, and they really enjoyed it, and it's easy to learn. And as you can see in the video, these are some of the examples of the works created by the user. So this is a work we make using that's generating papercraft as the output of the digital interaction. And then I also look at how to detect the inputs, which is a more straightforward way. So we think that we should avoid explicit additional additions to the paper material. Hopefully we can avoid the complex hardware sensors and visual markers. And also, hopefully, to use the physical papercraft to control the virtual contents. So I developed this algorithm a long time back. It's using the natural feature tracking, computer vision-based algorithm to recognize how people, how users fold the paper. So first, it detects the feature points in a piece of paper. They can use any paper, for example, a photo from the newspaper, etc., etc. So detect the feature points in the front face and the back of the paper, and then we divide the paper into different regions that most likely to be folded by the user. And then we can detect the folding by tracking the feature points on the paper. So we developed this proof of concept, a game that the user can use a piece of paper to play. So they can fold a paper and create some virtual objects in the game. So you can see here the user starts to fold the paper. And create the objects. That the algorithm detected the shape of the paper folding and generate a similar objects in the game. So you can recognize different types of paper folding. So, so this is the algorithm. We detect the feature points. Then basically we use a sift algorithm to extract the feature point and recognize them and track them. So this algorithm can actually recognize 5 different types of fundamental paper folding, and from these 5 different types of paper folding, it can be expanded to more complex shapes of folding. So these are 2 of the works I have done to explore the space of technology-enhanced papercraft. So as we can use paper as a type of tangible user interface to interact with the computer, the affordance of paper could also provide important inspirations to other interactive contexts, such as mobile interfaces or wearable interfaces or virtual reality. So in the rest of the presentation, I will show 2 projects that I explore the affordance of folding in these 2 directions. First project I want to share is a project called Origami. We borrowed the concept of paper folding to design a new type of smartwatch. So the motivation is smartwatch is really getting more and more popular, but its screen is really small. The interaction space is very small with the smartwatch. So we are inspired by paper folding interaction, design wrist origami. As you can see here, there are different multiple panels of the watch. You can fold and unfold to expand the interaction space of the watch. So this is a 3D design, 3D model for these concepts. And for the implementation, we embed basically touch sensors and accelerometers into different panels. And it supports folding, and it also supports flipping the panel and also pulling the panel out from the center. So we designed these 3 interaction techniques. And we also developed some application examples, such as a large keyboard. You can enlarge the keyboard of the watch by unfold the panel. And you can also toggle a map view, and you can also fold it back to the center to toggle different functions. And this application example is actually we conduct user studies. We ask users to propose their own what kind of application they would like with this form factor. For example, a 360 view of the photo and multiple user interaction on a smartwatch. So this work was published, I think, 2 years ago in the ACM Designing Interactive System Conference. And the last project I want to share with you is actually called HapTwist, which we have just done last year. And it was shown in Tokyo last December as a demo, and will be presented in UK, Glasgow, UK this May. In CHI conference. In this project, we are actually also inspired by the foldable objects. We borrow these interactions into virtual reality to allow users to have the haptic feelings in the virtual reality. So again, the motivation is we try to solve problems in virtual reality. Usually we can see very like realistic visual, and we can hear realistic sound, but other than that, we can't touch it. When we approach to some object, we can't touch the object. So we want to use physical objects to provide some touch feelings to the user in virtual reality. So we developed this HapTwist. So it's actually a software interface that allows the user to import a 3D model of the virtual objects and teach the user to create a physical replication using some foldable structures. And then you can use this replication in the virtual reality. So this is actually inspired by this kind of toys. It's called Rubik's Twist. It's a foldable mechanism. Although it's not paper, but it's similar to paper, it's foldable. You can create 2D or 3D shapes using these kind of objects. So in this system, we actually analyze the geometry information, 3D geometry of virtual objects, and turn this virtual object into the form of Rubik's Twist. So this is the architecture of these two kits. So the user can load a 3D model, and our algorithm will basically visualize the 3D model and partition them, and then transform them into the structure of Rubik's Twist, and then teach the user how to fold it, and generate a set of scripts that the user can import into the virtual reality, and use the Rubik's Twist structure to control and interact in the virtual reality. And this video shows a flow of using toolkits. So the user can import a shape, and it generates the plan of folding the Rubik's Twist. And the user can also do some annotations of the interactivity with the shape. And the system generates scripts user can directly import into their games. And then they also can also follow the structure to fold the physical shape. And then they can use the physical objects in the game. And when they touch the object, they feel that, okay, when I see this object, I also touch it. As I am a researcher in human-computer interaction, we always invent something, then we test whether user accept our system. Then we test the sense of presence, meaning the realistic feelings of using our objects in the virtual reality. And we found that, luckily, users feel very similar with our system output and the real object. They are both significantly better than the existing controller. And here are some more examples. I will end my talk with more examples in this process. For example, you can create a ping pong paddle to play games in the virtual reality, or steering wheel for driving, or multiple different objects in a farming game. For example, a fishing stick. Basically, these objects are all generated by our system and algorithm. Okay, with this, I want to end my presentation, and thank you very much. Thank you.